Hello. Yeah. You can share the slide.
Yeah, absolutely. Here you are. Sorry, actually, I think it was not
It's
right.
coming.
Sure. Can you
It's
see it?
still loading, I guess. Oh yeah. No, it's fine.
Is it okay? Great.
Yeah, that's fine.
All right. So I will just save some bandwidth, if you don't mind. Can you still see the slide?
Yes, we can see the full page of the slide. Yeah.
Okay, great. So let's start. Well, the goal of my paper was to try approaching about thinking and writing on quantum computing systems by adopting the same symbolisms and reasoning principles that are used by formal methods in software engineering. One of the objections that I heard about using formal methods in quantum computing was, what does the software engineering gain from representing the Hadamard gate as a Z scheme instead than as a usual matrix? It is not clear its added value when compared with usual description of these elements as matrices and quantum circuits. Well, the theory of quantum computing requires that we commence a conceptual shift from the current classical deterministic paradigms to the quantum non-deterministic paradigms, which, by relying on quantum mechanics, are not easy to deliver. But the use of formal methods can help those who work in the field of classical computing, first of all, in both understanding and reasoning about the properties of quantum systems by employing some classical tools of software engineering, used too already, and also to describe quantum structures and design quantum algorithms in a more spontaneous way, while still adopting a particular kind of mathematically rigorous technique. Plus, we underline that if we design a quantum computing system with the means of a formal specification, we are in fact developing a set of theorems about that system, which, by being proved correct, shall beforehand assure the correct behavior of the system. So formal methods are not just another way to representing a quantum computing system or one of its components, like instead matrices or quantum circuits do. Formal methods are a way to both represent a quantum computing system and to show that our system will do what we intend it to do. Formal methods make us confront the hard problems early. The difficulties cannot keep it, only defer it. By making difficult issues more visible, formal methods encourage us to seek a more thorough understanding of the problem we are trying to solve. They require us to express our intentions with exceptional simplicity and clarity. They help us resist the usual tendency in programming to make things too complicated and therefore error-prone and difficult to use. This last period was an excerpt from The Way of Z by Jonathan Jackie. It was taught for classical computing, but you can see how it very well suits quantum computing too. As you can guess, in our work, we adopted Z as the formal specification language of choice, not only because it is already the most or one of the most widely used formal language for describing and modeling the classical computing systems, but, and here we again pick from The Way of Z, most of the mathematics we need for formal methods is not terribly difficult. The discrete mathematics used in most practical applications of formal methods is easier than much of the calculus that students in the sciences and engineering must study. Z is based on type theory. a branch of symbolic logic that formalizes the notions of mathematical entities in terms of content, scope, and use, so that we not only have a formalization of the abouts of variables, functions, and sets and operations on them, but we also have a formalization of the idea that each entity is of some definite type, like, for example, the type of natural numbers. Thus, Z allows to reasoning over the properties of a system, be it inputs, transformations, outputs, or boundaries, by adopting a descriptive mathematical notation based on logical expressions that, altogether with well-defined data structures, permit to build clear specifications of the behavior of a system. In a nutshell, Z is well suited for quantum computing, not only because it is based on standard mathematical notations like those used in axiomatic set theory, in lambda calculus, and in first-order predicate logic, but also because it is already targeted at the clear specification of computer programs and computer-based systems in general. Furthermore, it contains a standardized catalog called the mathematical toolkit of commonly used mathematical functions and predicates that have been defined using Z itself. Therefore, given that...
Sorry, Carmelo, have you changed the slides? Because I still see the one.
I will come in a short while with a new one.
Oh, okay, sorry, just double check, sorry.
Sorry for making you concerned.
Yeah.
So, given that ahead of using an object in Z, we are required to formalize that object, all we need to do in order to introducing Z in quantum computing is to expand the existing mathematical toolkit by just two new entities, the observable and the observable operators. Henceforth, Z can support the stepwise construction of any quantum computing model, that is the abstract representation of a quantum computing system, through a ladder of just 4 rigorous mathematical yet intuitive steps. The first one is the specification, that is the narrative of the quantum computer system and describes what the system should do. Therefore, we have the refinement, that is the iterative fine-tuning of the formal specification and produces the polished quantum computer system. We have then the proof that works us through the process to prove or disprove the properties of the quantum computer system against its formal specification, in order to demonstrate that the candidate system's design is correct. And finally, we have the implementation of such system, that is the conversion of the model specification into working code. So here we go for an example about formalizing, first of all, the observable. We know that by the third postulate of quantum mechanics, an observable which has a finite number of quantum states can be represented with an Hermitian matrix. As such, the 3 requirements that it must have can be described in Z with some formalism by adopting strongly typed data in first-order logic. So, first of all, we shall declare our new type as a complex square matrix of order n. And we follow by declaring it as being equivalent to its own conjugate transport. You can see it in the second row here. And finally, we say that for every eigenvector of the matrix, the eigenvalue must be a real number, and such that it is the element on the main diagonal of the matrix. In Z, can yet be summarized with an axiomatic definition. So you can see the declaration on top and our definitions. We introduce the variables that must belong, actually, and the constraint on the variables that belong to the new object, and how they relate to each other. So the first step should be to formalize the observable as a new type that we call a big O. And after having introduced this new type in our catalog, we shall also be able to introduce the axiomatic definition of the most common observable operators, quantum gates, that perform unitary transformations on observables. And they both shall represent our quantum computing, both, I mean, observable and observable operators, the mathematical toolkit for designing quantum programs in Z. it is easy to recognize that similarly to what happens in any conventional computation, also a quantum computation is just a sequence of gates applied in a particular order. In our case, we know that one single input is applied to simultaneously to all the basis states, and we can see it on the predicate part here. So we introduce a generic quantum gate, we call it ZG, with as a bijective function between two O-dimensional observables. We define the variable in the set of our matrix, and we define the relationship between each element of the source and the recipient of our relation. So this is an example, for example, of some common observable operators. Like you see, the identity gate is just taking two elements and putting them in a one-to-one relation with themselves, or for example, a polyx gate that shall just flip the state and so on. And same happens for other kind of gates, like for example the Hadamard gate that shall map any basis state to one qubit with balanced superposition and vice versa. As you can see, we can define and we can formalize these gates with Z, making this simple mathematical toolkit that has a very precise. Because with Z, we describe the algorithm through an axiomatic definition, either by writing the constraining predicate from the conventional direct representation, for example, which is sound but does turning perspective, or picking from the quantum circuit schema, we can capitalize our mathematical toolkit, therefore the axiomatic definitions of the observable operators, so we can describe the Deutsch algorithm that we choose as an example in a more concise or in a more specific way. The result from this is that actually we are able to offer a guidance by describing the algorithm through a sequence of formal operators for coding it directly following the stepwise logic represented. You can see below of the specification of the Deutsch algorithm a coding that was made in Haskell. You can see how you can straightforwardly go through the predicate into coding the algorithm. So actually, the goal of this paper was to see how you can formalize an observable and its operators with use of an axiomatic definitions in Z. Why? Because, you know, actually quantum computing is kind of relegated within a narrow circle of experts. The theory behind it is quite hard to grasp, and it means that we have a very shallow base of people that actually are able to understand or to work on quantum computers, and even worse, to understand what they do and the algorithms that first of all are the main source of quantum computing. So we think that the diffusion of quantum computing cannot be forever relegated within a narrow circle of experts. But unfortunately, many computer scientists and software engineers who are entering the field of quantum computing are quickly put off because of the existing conceptual and notational barriers. And this is not only due to the intrinsic difficulty of the subject, but also because it can only be seen through a dark glass, because the complete knowledge of the state of the quantum system is forbidden. And formal methods, we believe, that can help to make that glass a little bit more transparent. So, as we have shown, one of the possible ways to overcome this stasis in the field is to just introduce, within the mathematical toolkit of Z, two newly formed quantum computing objects, so that the main notions of quantum computing can take the form of axiomatic definitions in the Z notation that is actually a language that should be very well known to classical software engineers, and that can be used throughout specifications. This approach ideally could open the doors of quantum computing to a wider audience of players, helping them to understand, describe, and effortlessly, we hope, translating the structure of a quantum algorithm into fully working code, and why not maybe also being able to reasoning about new quantum algorithms, starting from specifications that are very well known to this classical base of experts. Thank you.
Thank you, Carmelo. Any questions? We have quite a lot of time because we don't actually have the presenter for the second paper. So any questions?
Can I make a comment?
Yes.
Yeah, of course.
I'm a computer scientist, started my life as a computer scientist and ended up working in quantum computing, quantum algorithms, quantum models of computation. While I agree with pretty much everything you said in your presentation, I'm not sure that the barrier to entry is the notation. I don't think that rewriting quantum algorithms in Z will open the floodgates, as you're suggesting, and let this little field that's been relegated to very few experts, as you say, and open it up to the whole of quantum engineers in the world. The notation, once you get past it, it's really just linear algebra, the notation that is used by quantum algorithms people today. It's really just, bras and cats are just renamed linear operators. I don't think Z is that much more widely used. Yes, it's more widely used within the narrow, well, shouldn't say narrow, but by comparison, narrow field of software engineers. But in the greater computer science community, in the greater mathematics and STEM fields, I think linear algebra is much more widely used. But further than that, I think that the difficulty or the barrier to entry to working in quantum algorithms is the conceptual problem of thinking in terms of superpositions,
Right.
of interference patterns, of annihilation and creation, of not just using superpositions, but making sure that at the end you've constructively interfered the right solutions and you've destructively interfered the wrong solutions. That's really hard. That's the reason why there's very few algorithms, because we just don't have that intuition. And I don't think there's a magical bullet to give human beings that intuition. I think part of it is we just have to accept that quantum algorithms is hard. I mean, Bohr said it, Einstein said it, quantum physics is hard. And understanding quantum physics is hard. Trying to use it as a tool to solve problems, I think, is even harder. That's just something I wanted to say there.
Thank you for your thought. Well, I agree with you. The conceptual barrier is the hardest part about quantum computing, and I know it actually because, you know, I started working with quantum computation because of my thesis. And I found it extremely difficult to understand what is behind the curtain of quantum physics. But the problem, you know, well, it's not just about the notation itself. I've been working with many computer specialists. Most of them have studied linear algebra at the early stage of their formation. But once you work with computers, most of the time you stop using it. You start using the standard notations, let's say, of software engineers that can be, for example, you know, UML rather than Z rather than any other kind of notation that has little, actually, has more to do with shaping the system rather than mathematically defining the system. So when you have to get back to maths, because linear algebra, that is, well, it's not a killing subject, but when you have to define something that is so dark as quantum physics, in terms of something that you are not used anymore to reason about, it becomes, in my own opinion, makes everything much harder to grasp. And on top of that, the problem is that, as I said, formal methods are not just a way to give another way to shape a quantum system. They are also a way to prove the behavior of the quantum system, because you know, with matrices you can just represent an observable or an observable operator or a quantum system, but you don't know about what's the behavior. You have to guess the behavior. You have somehow to work in a number of attempts to pin down the behavior. This is something that formal methods do not allow you to do. You must clearly define the system with all of its components and with all of its behaviors, without giving any without giving any guess. You either know or you don't know. So for me today, you know, in quantum computing through Z made me better understand also how to work with quantum computing with matrices, with the classical direct notation, with wave functions. Somehow it is a kind, you know, of a way to map how I have been used to think in the past 20 years to something that was completely new to me. Not because I didn't study linear algebra, but because I was not applying it to quantum physics. And so it was easy for me, once I started to think in terms of formal methods, to say, okay, this is something that I have to imagine how it works. Let's see if I can put it in a way where I don't have to imagine anymore. I just have to read it, and it brings me to the solution somehow. Plus, in my opinion, once you are able to define an algorithm, for example, to a formal specification, as you could see in the last slide, you can go straight from the specification to the coding. I believe if I can just share for another second the slide. Well, actually, all right. For a software engineer or a standard, let's also say standard programmer. I don't know how many of you have started as programmers and then they have developed as software engineers or computer scientists. But try going from this, that is just the the Dutch algorithm expressed in a direct notation to an algorithm, to a code. For me, it was incredibly difficult. I find it much more easy to write the code from this instead. Because, as I said, it gives me exactly the steps that I have to follow to code the algorithm. So I very much agree with you. Writing quantum algorithms is extremely difficult because the problem is that you have to guess, to understand what is superposition, how interference works, so many things that we are not used to reason about in real world. But once you understand it, you also have to code that. And I find it quite challenging, going from just, you know, a quantum circuit rather than the specification of the quantum circuit in direct notation to the final code. This is just, you know, the experience from my own experience. I mean, this paper is just a way to put down my experience in a way that hopefully, you know, might help for more critical thinking about it. You're right. There is no magical bullet for learning quantum mechanics. It was a pretty hard way for me to go from zero to hero. Well, I'm not hero, however you know what I believe that there can be different other ways to express concepts that, if used, you know, in a notation that is closer to what you are used to employ in your job, probably for the past 20 years, it's difficult already to grasp the concepts of quantum physics. Think about having to grasp how to deliver the concepts of quantum physics in something that I'm not using since 20 years, since when I was a young and a more interesting guy. So this is just you know, my thought that I really hope can spur more thinking, more comments, and more critics, because that's where advancements come from comments, critics, and everything can be improved, of course. So sorry for taking too long.
No, we have a lot of time. No worries, Carmelo. Yes, thank you for sharing the personal experience. I think it's quite useful to the workshop. I think that is the objective workshop. So we still have 2 hands raised up. I think I will take Wolfgang's one and then followed by Shaka's question. Wolfgang, you can start.
Yeah, thanks. So I have one comment slash question. So I also believe that personally for me, and for likely also many students, that's my experience, that the notation as such in writing quantum algorithms is not the major problem. But when one thinks about it on a deeper level, when you think about the current knowledge in quantum computing in regards to, say, the complexity classes that are defined for quantum computers, what we know about the relationships between these complexity classes and the classical complexity classes, and the general question, what quantum computers can do better than classical computers, then we pretty quickly arrive at, like, okay, we know that most quantum algorithms use some known basic constructions like phase estimation, phase kickback, whatnot, but you don't really know where the extended power of quantum computers might come from. So we know that it might be entanglement, but then there are states that are too entangled to be useful. We know it might be related to superpositions, but then if you think about superpositions, what they mean, then it's nothing very special. Algebraically. So, and I think this is one of the very crucial points that we still need to solve in quantum computing and also quantum software engineering, to understand where the actual computational power of quantum computers comes from. And so the question is, do you think would describing things with well-defined semantics, with semantic techniques, probably be a chance to get a better understanding of why quantum computation works at all, regardless of specific notation and things like that.
Carmelo?
Yeah, sorry, I had a problem with connection. So I just was listening to you partially. I'm so sorry for that.
Okay, so basically my question was, do you think, so we still don't know a lot about why quantum computing actually works. So we know why some algorithms might work, why some techniques might work, but I think we still lack an understanding to pinpoint the power of quantum computing to really a number of explainable things. And my question was, do you think, and if yes, how that could be that formal methods could help us in capturing the very essence of quantum computing?
Well, I give you my own opinion, of course. I would actually divide from quantum software. As a software engineer, I don't really consider very much what's the platform my software works on. That's a middle to low level job that is for those who make compilers or interpreters. My task as a software engineer is to make a reliable and clear and a software that is reliable and with a clear specification that works with clear behaviors. Mm. This is already difficult in standard computing. I've adopted a number of tools during my career, and each tool has its weaknesses and strengths. Surely, doing it in quantum computing is even more difficult because the problem is not just the behavior of the software, it's also the behavior of the system. But I believe that this is something that should be probably clearly divided into specialties. Those who reason and think about the quantum software and the way to make it work correctly as it is intended to do. And those who have to put the software working on a real quantum system that actually you can make from many different theories. I mean, an observable can be ideally any property of any physical object. It can be an electron, and let's hope not, actually, because an electric field would make it change its state. It could be ideally be a water molecule. It could be anything. I should have to learn too much if I have to also focus on the system. That's why I believe that there should be quantum software engineers and quantum computer scientists as a clear division. You cannot know everything. You can understand something of the other field, but I believe that what you really need to do is to specialize two different fields. The one where I understand about algorithms and how to code them clearly, and those who to make sure that what is running on a quantum computer doesn't make any planet to disappear. This is my opinion.
So, yeah, that means that we also need to influence education, right? Computer science curriculum, to have quantum software courses and things like that.
Sorry, I didn't hear it well. Sorry.
So I meant that what you just said is a clear indication that we need to influence and to have quantum software engineering courses and curriculum and master degrees
I absolutely believe so. Yes, you're right. You got it very well. I believe so, because computer scientists have a very pure approach to computing. Software engineers make the dirty job somehow. Computer scientists are the elite about computing, and that's why I believe they should rather focus on the system more than on programming a system. It means to also being more close to a physicist rather than to an engineer.
Right. Yeah, I agree.
So yes, I believe that there should be this kind of courses that make that make people to be clearly prepared to what they really want to do. Be because they like it more, or because they're more lazy. For a computer science, maths is the everyday tool. For software engineers, maths is just something that you go through time by time. You mostly adopt theory, the theory of sets. You adopt block schemes. You adopt whatever makes you a critical thinker about the system. But we don't really use maths. So yes, I believe there should be specific courses for who wants to be a programmer on quantum software and who wants to be a quantum scientist on a quantum computer.
Yes, yeah, sorry. I noticed Shoka still have Shoka, do you want to ask?
Yeah, maybe. I think I was just wondering. Yeah, it's not some. I mean, for me, I was wondering about if, let's say, if we specify, for example, quantum programs in these formal notations, and then we want to do the things we typically do, right? In traditional, let's say, classical software engineering, such as model checking, theorem proving. So I was wondering that, are you also thinking along that that we have to go in that direction, or what? Because even we're doing, for example, model checking in classical computers, we always end up in space explosion. But if we want to do the similar kind of analysis in quantum programs or algorithm, it would be much more bigger problem. But what do you think? I mean,
well, let's say that there are many different kind of tools for describing a system. Z is something that I was introduced to during my university classes, and I found it quite not easy to grasp, but very close to how a software engineer reasons about the system. Of course, there is not only Z. You can find also formal methods like B, like VDM. You can express an algorithm in many different flavors, but the point about formal methods is that, as I said before, they are used to develop theorems about the system. You must prove that the system is correct beforehand, before you can really run it, really fire it. When I've started using Haskell, in programming quantum algorithms, it was an interesting aspect of learning quantum computing, because I was able to make just random tests. I could try. There is an interesting library from Green. It's called the QIO library, and it's written in Haskell. That gives you all the basic tools for quantum computing. And you can make all the tests you want. You can check, you can also try to write down an algorithm just by putting randomly gates one after another and see what happens. So this is how I learned, for example, programming something like 30 years ago. I was too lazy to go through the theory. I just liked to switch on my computer, open the compiler, and start making my experiments. And by making experiments without actually destroying anything, helped me a lot to scale the learning curve, because it was not just theory, it was practice. And from practice to theory, it was much easier for me to understand what I was going to do. Today, it's not possible to do the same thing with quantum computers. You need to understand the theory very, very well. You cannot just pretend that you can write an algorithm, pen and paper, because you just put down some random symbols and hope it works. But with this kind of libraries and formal methods, you can be brought to make experiments and probably to understand a little bit more what's behind the theory, or better, what the theory tries to tell us. I'm a great, I'm a great fan of experimenting. Theory is an important thing to do, but it's for pure minds. And in my own opinion, because of that, because you have, it slows down the development of some fields, because there is too much theory required. If you have the opportunity to give some tools for first making experiments to understand how it works, and then trying to reason about the theory behind what you have made, I believe the learning curve could be a little bit flattered. Not too much, of course, but it can be flattered. Maybe you can learn quantum mechanics in less than 10 years. It took to me something like 3.5 years from completing my classes to making my thesis, and were 3.5 years that I spent day by day, every day with a physicist to understand quantum mechanics before I could write one single word of my thesis. It was incredibly incredible in both ways. It was beautiful, and it was a nightmare altogether. If I had any tool for practicing and to see what happens, I think I would have been helped to understand the theory with an easier approach. That's just my point. Thanks God, the physicist I was working with, Dr. Wojtek Roga, is working with the Institute of Information and Communication Technologies of Japan today, was extremely patient with me, with all the craps I was doing. And he was never telling me, you don't understand quantum mechanics. He was always trying to find a way to say, yes, but. At the end, I grasped enough to write down a thesis and to, thanks God, get my degree instead of being kicked out of the university. And but not enough to say that I can understand quantum mechanics. That's something for really pure minds. I don't ever want to think that I'm a pure mind, but I just believe that you can put the two words closer as much as possible by giving practical tools for experimenting. Well, in making a building, you need architects, engineers, you need also the workers. Sometimes I've seen workers solve problems that architects were sure were unsolvable. Maybe that by chance, or maybe just because of the experience. They didn't know how to put, a solution into a project, but they knew the solution. That's the funny thing. So I believe that if you want to give to the field of quantum computing a greater chance to evolve, we should also give to the workers the practical tools to make experiments and maybe find solutions that actually may be thought to be simply unthinkable or impossible to be solved. But because, you know, when you think too much in terms of theory, sometimes you lose the exceptional help that practice can give. Don't know if it makes sense for you.
Yes. Thanks a lot, Carmelo. It was very interesting to hear your experience.